Ever stopped to wonder what gives your morning cup of coffee its magical kick? Well, look no further than caffeine, the world's most popular drug, behind that daily boost that most of us rely on. Caffeine is in fact the most popular psychoactive drug in the world. To put this into perspective, consider that over 100,000 metric tons of caffeine are consumed around the world every year. That's the equivalent of the weight of 14 Eiffel Towers. Coffee is actually made up by over 2,000 substances, but arguably the most important and well-known of all is caffeine. While most of this caffeine is consumed in coffee and tea, it's also ingested in some sodas, chocolate, and even beverages labeled decaf. The relationship between humans and caffeine actually spans centuries. The drinking of coffee began around 1,000 years ago in Ethiopia, later becoming popularized in Yemen. Caffeine became an integral part of these cultures. Tea and coffee actually arrived in Europe around the same time in the 16th century, and likely caused a revolution of knowledge and technology in Western civilization. This is because before caffeine's introduction, Europeans often drank weak beer and wine throughout the day instead of water due to unsanitary conditions. And while alcohol sterilized any germs, it also made people tipsy, affecting productivity. When coffee became popular, it not only allowed people to work more energetically, but also popularized coffee houses, where discussions about philosophy, science, and politics thrived. And without caffeine, Western civilization may very well be a lot less developed than it is now. Now moving on to the science of caffeine. To understand how caffeine works, we must first understand how our body makes energy. We've all heard that mitochondria is the powerhouse of the cell. That's actually because mitochondria produce adenosine triphosphate, or ATP for short, which is the primary energy currency of the cell. So that when ATP is broken down, it generates energy for the cells to be used. One of ATP's breakdown products is adenosine, which is ATP's chemical backbone. So as the body uses up energy, or ATP, throughout the day, adenosine levels steadily increase in the body. Now we need to understand what's going on inside the brain to make us feel asleep, to understand coffee's mechanism. Neurons are specialized structures in your brain, such as this one seen on the right firing away, and they have receptors which are perfectly tailored to adenosine, so that when adenosine docks these receptors, it activates a series of biochemical reactions that cause neurons to fire more sluggishly, and this makes you feel asleep. During sleep, the brain can actually replenish its energy reserves and eliminate adenosine. Eventually, not enough adenosine is left in the brain to activate adenosine receptors, so it makes you feel refreshed. So how does caffeine fit in the picture? The molecular structures of caffeine and adenosine are actually very similar, which means that caffeine can also bind to adenosine receptors. In fact, caffeine is what is called an adenosine receptor antagonist. This means that it's close enough to wedge into adenosine receptors, but not close enough to activate these receptors, so it doesn't make neurons fire sluggishly. So to summarize, adenosine inhibits your neurons, caffeine inhibits the inhibitor, so it stimulates you. So this is how caffeine makes you feel more alert. And caffeine's effect can usually only last 2 to 4 hours, depending on how fast your body breaks down caffeine, which is mainly determined by genetics. Once your body breaks down caffeine, adenosine can once again bind to its receptors and cause sleepiness. Caffeine also affects neurons where adenosine is linked to a receptor for another molecule called dopamine. One of dopamine's role in the body and brain is to promote feelings of pleasure. When adenosine docks in one of these paired receptors, it can make it harder for dopamine to fit in its own spot, interrupting its mood-lifting work. But when caffeine takes adenosine's place, it doesn't have the same effect and can actually make us feel happier because dopamine can slide in. Caffeine can also affect the adrenal glands above the kidney, which are seen here in yellow, because caffeine is able to block the action of an inhibitory protein known as phosphodiesterase. Inhibiting this enzyme, caffeine will increase biochemical signaling to allow the body to produce fight-or-flight hormones in the adrenal gland, such as adrenaline, which will ramp up the body's ability to burn fat. And it can also be used as a fuel for energy. This is slightly deviating from science, but because of the effects of caffeine on the adrenal gland, some sport associations think that caffeine actually gives athletes an unfair advantage because they have more fuel to use and more energy to burn fat efficiently. In fact, from 1972 until 2004, Olympic athletes were banned from consuming high dosage of caffeine to compete, showing how limits were placed on caffeine's consumption. Of course, not all of caffeine's effects are so helpful. After a few cups of coffee, we may not only experience effect in the brain and adrenal glands, but also the heart and the kidneys. This is actually because the heart also has adenosine receptors. And so just how activating adenosine receptors stimulating neurons decreases their activity, activating adenosine receptors in the heart also decreases its activity. So when caffeine binds, we can experience increased heart rate and also jitteriness because of these effects. The same is true for the kidneys, where binding of adenosine leads to regulation of urination. But when caffeine binds, more water is excreted by the kidneys, increasing urine production, while also making us feel dehydrated, as most fluid is lost rather than retained in the body during this process. What about those of us that drink multiple cups of coffee a day, or even energy drinks to keep studying? Your brain can actually adapt to regular consumption of caffeine by manufacturing new adenosine receptors if they are perpetually clogged. This effect is known as caffeine tolerance, and it explains why we need to consume more caffeine for the same effect to feel as alert if we constantly consume caffeine. So now, even if with caffeine around, adenosine can still do its job of signaling the brain to power down, so the sleep-inducing effects of adenosine may intensify. And this is why, if you suddenly quit caffeine, you may experience some unpleasant withdrawal symptoms, including headache, nausea, fatigue, and low mood. But in a few days, you'll feel just as alert as ever, as the extra adenosine receptors will disappear and your body will readjust. And just a note, you can minimize these symptoms by slowly weaning yourself off of caffeine rather than stopping abruptly. Now let's take a look at average caffeine consumption in common beverages and food. They range from 30 to 200 milligrams. However, since caffeine is indeed a drug, it does have a lethal dose. The lethal dose is actually 10 grams for an average size adult around 70 kilograms. And here you can see how this compares to the average caffeine content that we were just looking at before. So to be lethal, caffeine's equivalent in cups would be of around 100 cups of coffee, and you would have to drink those cups in a span of a very little amount of time, making it effectively impossible to overdose on caffeine, because you physically wouldn't be able to fit that much in your stomach in that amount of time. So we can say that caffeine is generally a safe drug, and it's very difficult to overdose on caffeine. Regardless, a few words of caution need to be addressed. Children should avoid caffeine because it's still unknown what effects caffeine has on the developing brain. And if you're constantly using caffeine to avoid sleep, you should stop because adequate sleep and rest are very important to healthy brain and function. Aside from its stimulatory effects, caffeine also has some therapeutic benefits. In fact, caffeine is often found with analgesics such as paracetamol and ibuprofen, because somehow caffeine can enhance their pain-killing properties, although this mechanism is poorly understood. There's also evidence that caffeine's effects on adenosine and dopamine receptors can have long-term benefits too. Moderate daily caffeine intake seems to prevent various neurodegenerative diseases, such as Alzheimer's and Parkinson's disease, because it seems to have some antioxidant and anti-inflammatory properties in the brain, which I personally find extremely exciting. So despite being a very tiny molecule, caffeine really has a big impact. From having sparked intellectual debates in old world coffee houses, to fueling late-night study sessions, especially during exam season. Regardless, thank you for joining me on this journey through the world of caffeine, and I hope you found some of this information useful, and will now look at your next cup of coffee with a new science-driven perspective.